We have already seen that the integral of sine x dx is negative cosine x plus c. Let's explore what's inside the integration symbol. The sine x dx on its own we know is called the differential. This we know from differential calculus. For now, the role of the dx is just to serve as an indication as to which variable you are integrating. For example, here we are integrating the variable x. Over here in the next example, we are integrating the variable u. And so the integral of sine u du is going to be negative cosine of u plus c. And you can predict that the integral of sine t dt is going to be negative cosine of t plus c. Now in general, we can come up with a rule that the integral of sine of anything, d anything, so for example, the integral of sine elephant, d elephant, is going to be cosine of elephant plus c. So here we've seen the role of the dx or the d elephant or the du as simply an indicator of which variable we are integrating. But it also has a meaning in the context of a differential. Let us review how exactly differentials work. Consider a circle with radius r. We know that the area of the circle is pi times r squared. Now, if I increase the radius of the circle by a very small amount, let's say that small amount is dr, what can I say about the additional area that I have added to the circle? Let's call this additional area dA. Now if I make a cut on this circle and roll it out so that it becomes a rectangle, we see that the inside area of this rectangle is dA, the width of this rectangle is dr, and the two lengths of the rectangle, one of them is 2 pi r and the other length is 2 pi r plus dr. Now yes, you're right. You may say this is not exactly a rectangle because 2 pi r plus dr is slightly bigger than 2 pi r. Now this is true, and therefore the area dA is always going to be slightly bigger than 2 pi r dr, which is the length of this rectangle times the width of the rectangle. But also we could say that the area dA is going to be slightly less than 2 pi r plus dr multiplied by dr, which is the longer length of the rectangle times the width of the rectangle. Expanding the right hand side of this inequality, we get that dA lies somewhere in between 2 pi r dr and 2 pi r dr plus dr squared. Now you must remember that dr is very exaggerated in my diagram. In reality, if we try to make dr as small as possible, like let's say dr approaches 0, as dr approaches 0, this term vanishes because since dr is small, dr squared is going to be even smaller. Think of if dr is 0.01, then dr squared is going to be 0.01 squared, which is much smaller than 0.01. And so as dr approaches 0, we can say that dA approaches 2 pi r dr. Let's see how this works out algebraically. We know the area of the circle is pi r squared, and if we want to find the rate of change of the area with respect to the radius, that is nothing but the derivative dA over dr. Now if we multiply both sides of this equation by dr, we get the same equation. dA is 2 pi r dr. This matches our geometrical understanding of dA. So dA is basically a measure of how much your area would change if your radius is changed by a very small amount dr. Just how we did it for the area of the circle, we can perform a similar analysis over here. Since ddx of x cubed is 3x squared, multiplying both sides by dx, we can say that the differential of x cubed, dx cubed, is going to be 3x squared dx. Similarly, since ddx of sine x is cosine x, d sine x would be cosine x dx. And you can try to work these out on your own. You should get d tan x is going to be secant squared x dx. Basically what we did is we differentiated tan x and then multiplied both sides by dx. And d3t squared is going to be 6t dt. Notice that we are using dt now and not dx. Finally, d ln t is going to be 1 over t dt. This idea of multiplying both sides by dx is going to play a very important role in the next few lessons of integration by substitution and integration by parts. So let's see, u is 4x squared plus 5. So we can say that du over dx is 8x. And multiplying both sides by dx, we get du equals 8x dx. Again, if u is equal to sine x, we've seen this example before, we can directly say that du is cosine x dx. I'm going to skip this step of writing du over dx as cosine x and then multiplying both sides by dx. You should be able to do that on your own. And if u is x plus 3 over 4, we can say that du is just going to be 1 over 4 dx. For the next example, we have a differential of an integral. So what you must always remember is that whenever you have a differential on the left hand side, you will always get a differential on the right hand side. For example, on the left hand side here I have a du, right hand side I have another differential 8x dx. 8x dx is a differential quantity. Similarly, we are going to expect a differential quantity on the right hand side, and that is simply going to be f of x dx. You can think of this d as cancelling out the integration symbol, but the differential is left intact. For the next example, let's recall the elephant rule of integration. If you remember, the integral of sine of elephant d elephant is cosine of elephant plus c. Applying that to this example, the integral of sine of x cubed dx cubed is going to be cosine of x cubed plus c. Similarly, the integral of secant squared root x d root x is going to be tangent of root x plus c. And the integral of x squared plus x to the power of 5 d x squared plus x is going to be x squared plus x to the power of 6 over 6 plus c. This is simply the power rule, treating x squared plus x as one unit. And finally, just how the d outside cancel the integration symbol. If you have an integral of a differential of a function, that's simply going to be the function itself. So f of x plus c. An example of this would be that the integral of dx, in this case the function is x. Remember, the integral of dx was x plus c. You can now pause the video and try to practice these examples on your own. Answers will be revealed in a few seconds.